So quickly recall. So basically, we don't really want to just introduce the formulas and done. But basically, we want to give you the motivation that helps you to establish these kind of calculation and ensure that they make sense. The establishment. So now you think back to the level integral. That's actually highly related to the line integral that you actually defining. Right? So basically, whatever curve that you have, the line integral is always parameterized so that directly relates to the level integral of a univariate function. So now, if you go backwards, this is to say, okay, you can generalize level integral onto whatever curve, right? So then we have a natural question. So how are we gonna generalize level integral that we have seen from the previous chapter? Right? So how does this generalize? So in the xy plane, we may have a region D, right? And we know how to do the double integral right now. So how are we gonna extend it to a integral on a general surface? Okay. Because so now we start with the line integrals, and we have seen, like I mentioned a little bit earlier, we have seen three different line integrals. Okay? So they are highly related to each other. So the first one is, in general, if you're given the vector field, you are actually doing the integral along the curve, starting the vector field with the tangent direction. So if you do the calculation, this is going to be the vector field evaluated along the vector function, and then you're starting with r prime, right? And then you're integrating with respect to t. So we also realize that we can write this as the unit tangent direction multiplying by the magnitude of r prime. So this is rewritten as the line integral along the curve of f starting with the unit tangent direction, and we're accumulating with respect to the r class, right? So this is the first line integral, and then we realize that okay, this is just a scalar. So this is a scalar function that is possibly having different values along the curve. So we can replace it by a scalar function in general. And it's accumulated with respect to the r class, right? And if we want to calculate it, this is going to be, again, parameterized from A to B. So we need to evaluate our univariate function along the curve. Okay, so basically evaluation along the curve. But now here, ds in the calculation, it will be replaced by the magnitude of r prime multiplying by dt. Okay. So this is the second line there. Right? And now the third one is more related to the geometry of your curve. C. Right? So if you are integrating one along the curve, this is going to give you exactly the integral for the calculation of the arc length. Right? Next. So these are the three line integrals that we have seen. So in this section, we're going to motivate also three different surface integrals. So of course, now, although we established this, we established these line integrals in the order of 1, 2, 3, but you see, okay, equation 3 is actually more fundamental in terms of its geometry. So, and the notation is more is similar, right? So we start by extending 3 idea of extending equation 3. So here we're going to extend it to a surface. Okay? So it's going to be the notation here is that we integrate over a surface. But now, if you think about the curve, so basically you do the subdivision of the arc length and you integrate that, right? So here, for a surface, how are we gonna divide up the area along the surface that you're given? So this is something we're going to establish. Here we just denoted as red square. And then on the right hand side, if you're looking at this, so this is actually basically integrating along the interval, which is the parameter from A to B, right? That's the parameter T here. So that's something we want to consider. So this somehow translates to a double integral eventually, okay? Because the surface is actually a two-dimensional object. So eventually you are going to translate it to a double integral. But then what's special here is that similar to this is going to be a vector function that we're integrating within the magnitude. So that's something we will establish. We just now put it as a star. And usually double integral will associate to the way that you subdivide the region. So eventually the calculation is like this. But we need to specify what that star is. Okay? And of course, now this calculation in equation 3 is about the arc length, right? So we expect that this calculation relates to the area of the surface that you start with. Okay? So we want to extend this area of the surface in this way. And then we can now continue with equation 2 on the above, okay? So the equation 2, the only difference here is that it's introducing a scalar function, little f, right? So now we also introduce that. So basically, it's going to be the integral on the surface. Now we are putting down that little f as a scalar function. So now still we're integrating. We want to specify what that square is. And so it's the same thing that we just put in another function there. And then we mentioned, okay, so you somehow want to so this is the parameterization for this surface S on the parameter set D, right? And then this part in equation 2, this is the evaluation of your function along the curve, right? So here you can expect you want to carry it over. So this is f. We are evaluating it on the surface, but then how are you going to parameterize the surface? So this is another thing that we want to study carefully. But then it follows with the same expression from above right here. Okay. So now the magnitude of some vector function and then dA. So that's so basically now you see in equation 2, what's new is the evaluation of the scalar function you have that we're going to study. Okay. And finally, we can now think about the vector field. So now here, the evaluation carries over to this. Okay. So basically, on cap f of RT, that's the vector field evaluated along the curve. So and this vector goes here. Okay. So that's going to be an inner product. Somehow we want to also establish for the surface integral. Now, if we want to extend 1, so it's going to be an integral on the surface S of now vector field starting with some, but here, let me quickly also come out. So that's dr. So this is a vector, right? Dr is a vector. So we want to also define this vector nicely. So that's something we also want to know what that is. And then So this is a question which is a little different from the double question mark, which is evaluation. But now it's the vector field being evaluated. So that's something similar to equation 2, okay? And finally, we want to do a dot. And then dA. Right. So basically here, in the one-dimensional case, you have R the curve and R prime, the tangent direction. But now, so for a surface, it's going to be a little bit more complicated. So the double question mark and the vector star there, they will be somehow a little different. So to give you a heads up, this double question mark is a two-dimensional representation of the surface, right? But then this star is essentially going to be so there will be two tangent directions, right? But then for a surface, it's going to be one normal direction. So that star essentially will be the normal direction. So that's going to involve a cross product. So everything comes together at the end of this course. Okay? So yeah, in a sense, I would say this is a lot of fun, but this is definitely more involved, more and more involved. So let us start with the simplest. Extending equation 3. And find the area of the surface, A of S, of a surface capacitor in R3. Question. A curve cap C can be described by the vector function of t, where t is a single parameter between A and B. Right? Now, in general, a surface S may be described by some function z equals to f of xy. Here, r of t is a vector valued function with variable t. Now, f of xy, this little f describing the surface is a scalar valued function. You see the difference here. So basically, for a surface that we're talking about right now, z of xy, actually, you input a pair of xy and you output the z value. Okay. So this is actually a scalar valued function with variables x and y. So here comes the question. How to describe a surface as a vector? So how do you describe a surface capacity in R3 using vector value functions. So, the short answer here is that we just put x, y, z all together in the vector representation. Okay? But here, to be more specific, let us increase the dimension from an interval from A to B in one dimensional to two dimensionals. For example, we just make it the combination of two intervals. So we define, it's kind of weird. Define vector valued function. So usually we used to have RT for a curve, right? Now for a surface, we're going to describe it as R of U and V. Okay, so there are two parameters U and V. So we describe X, Y, and Z, the three coordinates, all in terms of this new parameters U and V. And here, I would like to quickly mention that the choice of the two parameters U and V is not unique. Okay, so for a surface, you have many ways to describe it using two parameters. The above vector function R of UV also introduces geometry equations. So basically, if you don't write it as a vector function, you can write it as a parametric equation where you have x coordinate is defined by x of uv as a bivariate function. What is y equal to uv, which is defined in terms of the scalar function with respect to u and v, and z is similar. Okay. So now here we have three equations that are determined by these two parameters, right? Where this UV pair varies throughout a set that we call kappa in the two-dimensional space. So in the example we have right above, that's the combination of two intervals, right? The interval for the first variable, which is between A and B, the second between C and D. So this thing, as an example, it could be that two-dimensional rectangle. Okay. So let's look at some examples for this description of a surface. So basically, we just need to choose two parameters to describe that surface. Okay. Example. So let's look at R of UV, where this is actually 2 cosine UI plus Vj plus 2 sine of U. Okay. Okay. So basically, we have two parameters U and V. Now we're just describing a vector function in terms of these parameters. And we specify that U is between 0 and 2 pi. V is between 0 and 3. This is a parametric surface. So basically, we are parameterizing this surface in terms of U and V. Okay. So now let's identify the geometry pattern. So the parametric equations are straightforward. So basically, this is just saying, okay, we want to write out x, y, z in a specific way. So x is the first coordinate of your vector function, which is 2 cosine u. Y is v, and finally, the z coordinate must be 2 sine of u. Okay. And here, so that's the parametric equation, but we still want to specify the range of the parameters. So u is between 0 and 2 pi, and v is between 0 and 3. So now, in the geometric sense, you see, okay, y relies on v, right? X and z relies on u. So y is independent from x and y. Excuse me, y is independent from x and z. So that tells you this is kind of like a cylinder. Okay. We have that x squared plus z squared equals to 4. And so that's the relationship between x and z, right? But y is independent from x and z. Okay? So y only relies on v, right? This is actually what? This is actually, we just have a circle and we move it along the y direction for 3 units. Okay. So we start with a circle that's centered at the origin and has a radius 2. But then we extend it all the way at y equals 3, right there. Okay. So everywhere in between, you will have a circle. That's the same shape. Okay. So this is the surface of yours. So basically, we're looking at the cylindrical surface that's surrounding the cylinder with a circle basis. Okay. So basically, as a remark, we will write down as a fact that we are able to eliminate these variables u and v to get the equations that we just mentioned. That this is the cylindrical surface remark. So basically, we set up the 3 equations in terms of the parameters. And also we list, so basically that's the 3 equations that we have for the coordinates given the parameters. And then also we know that u is 3 between 0 and 2 pi. And v is 3 between 0 and 3. So, like we said, eliminate u and v will help you to find the 3-dimensional representation of this surface. Okay. So which is x squared plus z squared equals to 4, which is the same circle regardless of the y value, but here we have the y value cut between 0 and 3. So let's look at another example. Here, we want to parameterize and all. So what is the parametric representation? Of the surface equal to, let's say, square root of x squared plus y squared. So yeah, let's put a 2. So let's put a 2 in the front. So the constant actually just, if you think about it, this constant just relate to that angle phi, right, in the spherical coordinates. But here, let's just see. So essentially you have a cone, right? And it will just extend without bound all the way out. And then that's the d-axis. Then x and y. So actually, there are a few ways that we are able to parameterize this surface. Parametric equation on parametric representation. So recall, what do we want to do? We want to just set up the equations for x, y, z coordinates in terms of two parameters, okay? U and v. And here, the choice of u and v is really up to you. So you can say, okay, since z is relying on x and y, right? So what about choosing just x and y to be the parameters? So that's one option, right? So then you just need to also describe z in terms of these variables. Okay. So here, that's the intuitive one. So x equal to x, y equal to y, and these are the choices of the two parameters that we're using on the surface. So finally, we see, okay, now we just need to express z as a function of x and y. And if you feel that it's not comfortable to just look at x and y as the parameters, you can just, in another way, just choose u and v as the new parameters. But then, so u is the first parameter, v is the second, and then of course you just do the substitution so that everything is in place of u and v. So that's totally fine. But here, if you want to write down the vector function for the surface, it's really standard. We just put everything together in vector representation. Okay, so it's going to be ui. So basically, x component is now u, the y component is now v. Finally, the z component is the function expression in front of k. So basically, if you are just given a functional expression for the surface, then of course you can just do this straightforward parameterization. But of course, there's going to be the radical right here because of the formula of the cone. So, and another parametric representation is related to the elimination of this radical. So in case if you don't want the radical and you know, okay, so this cone is actually really nice because we have seen that this is a symmetric object that's in terms of the z coordinate, right? So in terms of the z-axis, and you do the evolution whatever way you want, it's always the same thing. That tells you, okay, I can do cylindrical description. So my z coordinate will just not be changing for the entire time, right? So that the rotation is actually the angle theta, right? So here use cylindrical. coordinates. So basically, we just let x and y to be r cosine theta and r sine theta, respectively. And finally, we just want to substitute x and y into z to make the z coordinate in terms of r and theta. Okay. In terms of the new parameters. So square root. Okay, now x squared plus y squared, we know that's r squared. So that's pretty nice. And as long as you make sure that r is always defined to be non-negative, then we just get rid of the radical. Okay. Thus, we have another vector function representation. And now it's in terms of r and theta. So if you okay, so I would need to admit that this is a kind of abused notation. So r is the vector for the vector function, but now we have another r that's the parameter. But you know what it means. Okay, so basically this vector function in terms of r and theta is going to be, so basically we just put the coordinates all together in the vector form. So r cosine theta in front of I plus r sine theta in front of j, and finally we just need to put the z coordinate there. So it's 2r. Okay. So that's good. Okay. So here we just see, okay, as long as we put the things all together in using two variables, everything. And of course, now you see, okay, I have the first representation to be the straightforward one, right? The second representation to be the cylindrical one, right? But then if you think about, so of course there's going to be a third, but it's not really required for you to know. But you can think about it, right? So what about spherical coordinates? So you know, for the cone right here, you know that this angle of rotation from z-axis to the surface is actually a fixed. It's a fixed radian, right? So this p relates to this in this triangle. This the opposite edge has 1 as the distance, and the adjacent is actually 2, right? So z equals to 2 times the radius. So that's something special. So that tells you the angle, and then you know, okay, if you are doing spherical, then this rho and theta will be changing. Okay? But essentially, it's the same idea as the quadratic equation representation 2, where you cylindrical. So that we will not write down. But basically, you do have a lot of choices. Okay? But always specify the range. So theta, we need to specify to be between 0 and 2 pi. So as expected, because you can do the rotation whatever way you want. And we want to also ensure that r is non-negative so that you can get rid of the radical in a straightforward way. Right. Another example. So let's think about the parametric representation of the sphere. So if you recall, the sphere is not easily representable by x and y, right? Because the sphere, there are two pieces, the upper piece and lower piece. And if you're doing that representation in terms of x and y, it's on the large radical, and then you will have to divide the region in terms of x and y carefully because it's a circle, right? So it's going to be reasonable to utilize the spherical coordinates. Okay. So let's say the radius is 2. So x squared plus y squared plus z squared is 4. So using spherical coordinates, we have, so rho is the distance from the surface to the origin. Okay. So that's a 2. It is the radius of the sphere. But now, so in the spherical coordinates, you know rho is fixed, right? But then we just know by default, theta is free between 0 and 2 pi, and p is between 0 and pi, right? So we just put them there. And hence we have x equal to 2. So rho is 2, okay? So rho cosine, excuse me, sine phi cosine theta. Just remember what that formula is. Y is 2 sine phi sine theta. Finally, z is 2 cosine phi. And specify that theta is again between 0 and 2 pi. Here, phi is also free within the original interval from 0. So that's good. So here, basically, for the spherical coordinates, now we're fixing the distance from the surface to the origin to be 2. Right? So that's eliminating one of the parameters in the spherical coordinates. And let's look at another one. Example, parametric equation of a plane that passes through, let's say, P0 in the 3-dimensional space with position vector R0. In other words, we have this vector R0 to be the vector from the origin to the point P0. Okay. So we know that the plane here passes through this point P0, and this plane is parallel to 2 directions. Which are vectors A and B. So basically, 2 directions and the point can define your plane, right? As long as we assume that the 2 directions do not parallel. So A and B here are not. So geometrically speaking, you have a plane. Okay. So let's quickly sketch the figure. X, Y, origin, Z. So we know there's a point on the plane, so that's called P0. And then, so the vector R0 is actually the vector with the head at the point P0 and the tail to be the origin. So actually, I'll just draw the arrow. Okay, so it's supposed to be straight, but yeah, I hope you get the point. All right. So now basically we want to parameterize whatever point on the plane, right? So arbitrary point, let's put it right. So that's the point P that we want to describe. So as a vector function, we want to describe this vector from the origin to this red point. And what else do we know? We know that there are 2 directions A and B parallel to this plane, right? So basically, that's just telling you you have 2 directions within the plane. Okay. So we can put them together with the tail to be at P0. Okay, so you can have let's say this is vector A. We have another vector B. Let me pull it down. So this is B. So basically, as long as we know how to describe this vector P0P within this plane, okay, then we can describe OP. Right. So we know OP equals to OP0 plus P0P by triangle, right? So we know that OP0 is exactly R0 that we start with, okay, the position vector. So as long as we describe this vector in terms of A and B, that'll be good. Right? So if that's clear, then we just look at what happens within the plane. Okay? So essentially, now these vectors P, so this vector A, B, and this vector P0P that we want, we are having these within the same plane, and they have the same tail. Okay, so let's say this. So if you zoom in within the plane, we have the vector A and B here. So these are the information that we know, right? So P0. So and the red point P is here. Okay. So how do we describe this vector P0P in terms of A and B? So this is now back to the beginning of the semester, right? So basically we have the parallelogram rule that tells you basically what you do is you draw a parallelogram that has the diagonal to be this vector P0P, right? So in other words, you can just do the parallel edge that's formed by the point P, which are parallel to the vectors A and B. Okay? So just now I have drawn an edge that's parallel to A, but now I'm drawing the one that's parallel to B. Right? So this forms you a parallelogram, and these two edges starting from the point P0. Okay, so these two vectors in red, they are just scalar modifications of the original vectors A and B. Right? So you can say, okay, this red one on the left, this is UA. So on the right, this is VB. Okay? So basically, now you see this is a coordinate system where U and V, they're just scalar multipliers in front of the vectors A and B for you to represent P0P. Okay? So now as long as you have these parallelogram, then you know P0P equals to the two red vectors as a sum. So it's going to be UA plus V. Right? And you see, okay, U and V, they're just scalars and they're the parameters describing whatever vector that you have within the plane. Right? Okay, now we do have everything. For any point P on the plane, since we can represent P0P as UA plus VB, for the parameters U and V. Right? So these are the two parameters that we need to describe the plane. For parameters U and V. So we put the things together. Okay? So on the upper right corner we have P0 equal to P excuse me, OP equals to OP0 plus P0P. Okay? And we just do the substitution. So OP0 is R0, right? And then plus P0P is now UA plus VB. We'll directly substitute. So these are the two parameters u and v, then they are just any real numbers. Therefore, the vector valued function of the plane is exactly the equation that we have from the previous line. So if we once again name it to be R in terms of u and v, so I'm gonna cheat by copying this part. And here, so if you're looking at the entire plane, then u and v are just free between within the entire the set of reals. Okay. So now further, if we know that vector A is having coordinates A1, A2, A3, and B is having coordinates B1, B2, B1, B2, B3, and finally, that's R0, we have coordinates to be X0, Y0, Z0. Then we can explicitly write out the parametric equation. Okay. The parametric equation of the plane is just basically expressing x, y, z components as separate equations. So we just match the coordinates, right? So x equal to x0 plus ua a1 plus v1, and this component-wise matching. So y coordinate is the sum of y0 plus u a2 plus v2. The z coordinate must be z0 plus u a3 plus v. All right. So here, now we see, okay, basically, if you recall, in the first chapter, when we were talking about the plane, we have the vector equation of the plane, right? So which is a little bit different from the vector function representation of the plane, okay? So this one is a little bit different, but essentially, they are representing the same thing because by the nature of that definition, we know for the equation of the plane, what's important is the null vector, right? And you know how we got the null vector, which is A cross B. Okay? So that's something we have seen already. So the vector equation of the plane is actually, if you recall, is null vector n starting with r minus r0 equal to 0, right? And further, if you simplify, you will get that standard equation of the plane. Okay, but here we know that this null vector is the vector that is perpendicular to both A and B, right? So now we have the plane equation in the vector function form on the top, right? So indeed, it will satisfy this dot product equation as a vector equation, because note that our vector valued function for the plane is, so basically R UV equals to, let's write it again because this is the equation on the top. So the initial position R0 plus UA plus PB. Right? And actually, it's really simple to verify the vector equation in the previous line, because indeed, now here, if you do the substitution and starting with the vector function RQB minus R0, so here, this directly equals to basically now we know n is a cross between A and B, right? And now we're starting what? We're starting so R minus R0 is exactly a vector within the plane, which is UA plus BB. Okay? Any combination between the vectors A and B. And here you can already know, okay, so this vector must be perpendicular to the combination of the vectors A and B, right? But here, if you want to do the substitute, if you do the distribution, so the cross, you can distribute it to be the starting with UA and starting with BB, right? And now, okay, so now every part is a zero, right? Because you know, okay, A cross B is perpendicular to both A and B. So indeed, so these two representations are essentially equivalent. Okay? So A cross B is perpendicular to both A and B. So I make the leave space, right? The next line. So you see that the emphasis is a little bit different. So at the beginning of the semester, this equation for the plane is actually one description, okay, as a geometric object. But now here, if you want to parameterize, we have to use two parameters as a surface, okay, but essentially they are the same thing. Another example. Parametric equation for the surface generated by evolution by rotating a curve. So let's say we have a curve, which is a graph of a function. So let's say this is y equal to sine of x, and here we have x between 0 and 2 pi. So you have just one period of the sine function. Okay? But now we want to rotate it with respect to the x-axis. So here, let's quickly do the illustration. So basically, you have a function like this. So one period of the sine function. Okay, so you know, okay, it has intercepts, x-intercept should be pi and 2 pi right here. Okay. And then there's the highest output to be 1, the lowest is -1, and they will occur at pi over 2 and 3 pi over 2, right? So now, so this is the graph of the function, right? But then if you rotate about the x-axis, then essentially, if you recall what you have learned in Calc 2, so basically for whatever vertical bar that you have, it will rotate your circle, right? So to illustrate, so basically the evolution is like this, right? So basically, if you just do the rotation and you get the z-axis as perpendicular to the xy plane, then the xz trace is going to be the same thing. Okay? So essentially, you can imagine that you will have like two football-shaped solids. So okay, so here let's just put the y-axis so that it's pointing at the back of the screen. So essentially, in the xy plane, the thing is, if you do the entire rotation, you will have this piece, which is exactly the negation of the sine function. Okay, so basically, these two shapes will be evoluted, so you will have two solids like that. And to sketch, it's going to be like this. And then essentially we'll have circles. So for a vertical bar, like right here, then it will evolve to a circle. I will evolve you a circle. And the radius here is exactly that functional value here. Okay. So let's say this is the x value. Let's say this is x0. Yeah, and get an arrow. So let's say this is x0. So this is x0. Okay. So the radius is sine of x0. Okay. So this is the height. And of course, if you talk about these highest points, they will give you the largest circles. So if you want to take a closer look at these cross section as a circle, so let's quickly get a figure for that. So essentially, like we said, you have the vertical bar in red, right? But then you just do the evolution of the around the x-axis. So in the YZ plane, you will just have a circle. And put it in here. So YZ plane. So this is the circle with radius to be sine of x0. And the thing here is that essentially, well, we are looking at the x values between 0 and pi. So you have a positive radius. But basically that's actually saying you are starting at the point on the positive side of the y-axis, and you're doing the evolution like right there. So so basically there's a rotation angle that's theta, right? So somehow you need to incorporate that in your parameterization. Right? But then suppose you can expect that if you have the vertical bar right here that tells you, okay, my y value is negative, then I'll be starting from this point in purple, and then I'll be just doing the same evolution. That is just gonna get me to the negative side of the z-axis, and then so on and so forth. So it's always a one period that you are doing the rotation. Okay? So you can expect when you're describing this using two parameters, one of the parameters is definitely x, right? The other one is just rotation. So we just put down the description. So we have, so one of the parameters is x, of course, The other one is the rotation theta, right? So basically for this rotated point in red, so let me put this arrow more accurately. So this point, so the y-z coordinates, they both so the y-z coordinates, they both rely on theta, right? So y here is sine x cosine theta, z is sine x sine theta, right? Just like what you do with the polar coordinates, you are just replacing that r by the radius right here. Okay, so yeah, let me put a bracket to indicate, okay, that's the radius that we have captured from the original function. And here we just specify that, okay, x must be between 0 and 2 pi. So that's the original range of the x value. But theta is between 0 and 2 pi as well. Okay. Because you do the rotation, it will include the entire circle. So it's good. So this is a sine function, right? In general, you can expect that for whatever function that you have, you can also do this rotation and get the parametric surface. Okay. So we mark the surface has obtained by rotating the curve y equals straight from x, where my x is cut between some constant a and b about the x-axis is, so it's the same idea. So you see that functional value is now the radius of the circle that you obtain through the evolution. So x is one of the parameters, and y now is described by the radius times cosine theta. Z is that same radius times sine theta. Due to the upper right figure in the picture, right? So that's just the circle that you form when you do the evolution. And here, once again, x is cut between a and b. That's just expected. And the theta, you have to have it within one period of rotation. Such surfaces are called surfaces of revolution. So you basically in Calc 2, you can recall that we were trying to calculate something out of the surface of revolution. Here we are just doing it as a parameterized description. Okay, so which is a little different. Similar parametric representations can be obtained. Solid. Rotating with respect to other axes. So if you're doing the evolution about the y-axis or z-axis, it's essentially the same. And you just need to carefully parameterize it. You need to carefully parameterize that circle that you form. Okay. All right. So Now, that's pretty much all we need to discuss about the introduction of the parameterized surfaces. Okay? But if you think about the motivation of this section, you see, okay, we are trying to do what? We're trying to do the surface integral, right? So actually, we are starting with the integral of the area of the surface. Okay, so how are we going to calculate the surface area? So that's the first essential topic in this section. Suppose, so of course, we want to start with some kind of parameterization of a surface, but then we're going to calculate. Okay? And the way that we calculate is, once again, starting from the Riemann sum estimation, and we accumulate this integral. So suppose we have a parametric surface. Fs, and we have two parameters. So this is R of UV, which equals to X of UV, I plus Y of UV, J plus Z of UV. Okay. So basically, every component now is described in terms of U and V, and we specify a region for U and V. Okay. So it could be a rectangle, it could be a circle, it could be whatever the region that you want, as long as you can describe it within the UV plane. Okay. And here comes the question: how to compute the area A of S for the surface? Okay. So basically, if you think about this, what you know is the region D, that's in terms of the parameters U and V. But now, in a sense, it will map to a surface using this rule, right? And then you actually want to compute somehow the mapped area of on the surface for the region. Okay? So what actually does it look like? So essentially, you have a surface like something like this. Okay? So let's suppose that the region D is determined. So the entire surface looks like this. Okay? So it's something curvy in the three-dimensional space. So here's what we're going to do. So basically, we subdivide the region D. Okay, and now let's just start by assuming that the region D is a rectangle, and then essentially we're going to have to subdivide it into pieces, right? So let's say for representative, we have a point right here. So this is actually relating to the point U0, V0 for the parameters. So as a vector, it goes like this. Okay. And now, if you think about this as one of the corners of the rectangles in terms of the UV variables, right? But it's just by doing this the subdivision of U and V intervals. And then basically, if you fix U, let's say you have you are lying on a curve. Okay? So if you fix the first coordinate and then changing the second, you may lie on this curve. So this is where we change. So let's call it C2. So you're changing the second coordinate. Okay? So if you think about this, say, okay, I fix U0, but I let V to change. So this is actually a curve, right? And similarly, if I allow the first coordinate to change and the second coordinate to fix as V0, I may end up with another curve like this, and we call C1. Right? So basically, here, starting from a point, if you just change the first variable, you may end up with a curve which we call C1. And then there's another curve we call C2 if you just change the other variable. Okay. But now, basically, this is the starting point. And then if you slightly change the U0 value, you may end up with another piece of the curve, which is, you can say a little bit parallel in this figure as a curve. And then if you slightly change U0, you may end up with this another edge. So we are trying to estimate the area that's shaded right here. So this is the subpiece of a region on the surface. As long as we are able to describe it, then we will accumulate everything. Okay. And here you see how we get those. So basically, we just fix one of the variables like we are doing partial derivatives. Right? So that's exactly what we do. So if you zoom in, the region that's shaded. So essentially, it's really a similar idea. So let's say we start. So the corner here is that vector R U0 V0, right? And then, okay, basically we have two sides along the curve C1 and C2. So we're gonna say that segment, that arc, okay, that's curvy arc is along C2 and on C1 like these, okay? And they have arc length that's somehow related to the amount that should deviate from U0 and V0. Okay? And now, basically, if you know this arc, and if you get an angle, you can approximate the area, like using a parallelogram, right? So here, how to estimate the arc length? So that definitely relates to the tangent direction, right? So these are two curves. So once again, let me copy it down. We have C1 and C2. So what do you think about the description of the tangent direction? So that's partial derivative, right? So let me name so along C1, the tangent direction is the partial derivative with respect to U, right? So let me write that down before I actually go. Because C1 is saying, okay, I allow you to change U, right? So that's the only parameter. So if you are getting the tangent direction along the curve at the point, that's exactly doing the rate of change with respect to the variable U, which we just name it as R sub U, because that's the partial. Okay? And similarly for this one, you're only changing the V variable. So this is R sub V. Okay? That's the tangent direction along the curve C2. Okay? Okay, just to recall, what do we want to do? We want to estimate for a small increment of the area, if you slightly increase the U value from U0 to some U0 plus delta U. And then also at the same time increase the V value from V0 to by the delta V units. Okay. So if you increase the input pairs, okay, within the region D, then that will result in a small region on the surface. And then what do we want to do? We want to somehow estimate the arc length right here and the arc length right here, and also okay, these are two curved edges, right? We want to get an angle, so we are able to estimate the area. Okay, but now basically the idea here is that we're using the tangent directions in red, okay, to approximate these edges on the sides, okay, curvy edges on the sides. So basically, if you recall, on the right hand side we have a curve and its tangent direction, and we know that we can utilize the tangent direction to approximate the arc length along that curve. Okay? So that's what we have seen. So now we're just going to do it systematically, since we have two variables U and V. So we have the partials along two curves. Okay. Just be reminded that C1 is a curve that the U variable is changing, but V is staying as V0, okay? So basically, this is the partial that you can do that's about the variable U. Okay, so that's why we denote it as R sub U. Here, R sub U and R sub V are vector functions, okay? So are vectors. So just by doing the partial derivative with respect to U, we will have del x del U evaluated at U0, V0, I plus del y del U at the point plus del z del U at the point. So basically, just recall, okay, so R, this is the vector function with components x, y, z, okay, in terms of parameters u and v. So here we can do the partial with respect to u, and similarly, you can expect that R sub v is just doing the partial with respect to v. Okay. So we can just check here by replacing the partials to be in terms of v. Okay, so that's a little bit special here. So you see, this just carries along the idea of the tangent direction along a curve, but now here we have two directions. Okay, we have u and v, the two variables. So there are two partials that we can do here. Okay. Indeed. So these are the R sub u and R sub v are along the tangent directions of the curve C1 and C2, right? Respectively. Okay. So now, like I said earlier, so we now have the vectors R sub u and R sub v in red, right? So here we actually want to calculate the area of that surface on the left hand side. Okay, that's a small region, right? So here we're going to utilize the increment of the variables delta u and delta v also along the tangent directions. Okay. So let me let's see. Let's quickly copy this region once again. So basically, we want the region, we want to approximate the area. But then, okay, we utilize these tangent directions, okay? So basically, just recall, so the edges here from C1 to this curve, we increase the u value to let's see. Actually, this is v, right? So this is the direction along which you change v. So this is increasing delta v units. So you're traveling along the curve C2, but then it's going to be the vector along the tangent direction of C2 multiplied by the amount that you increment the second variable. Okay, so this is actually delta v times R sub v. Okay, and similarly, from C2 to this side, we actually increase the u variable from u0 to by delta u units. Okay, so that's a scalar multiplying in front of that tangent direction. Okay, right. Scalar multiplication in front of vectors, right? Right. So basically, these are the vectors that are somehow estimating these curvy directions. That's the point. And now we want to estimate area, right? So the area we can approximate by just doing the cross product of these two vectors. Because that's actually giving you the area of a parallelogram that's formed by these two vectors. Okay? So just once again, we're using something that we know to approximate something we don't. Okay? So the right hand side, this area is an approximation of the curvy surface area that's a subpiece on the left. As long as the increment of the variables delta u and delta v are small enough, and so this approximation wouldn't be too bad. But then we just do the cross and we take the magnitude, right? So this is r sub u multiplying by delta u crossing r sub v multiplied by okay. So we know that these scalars delta u and delta v they are just positive numbers that we take out of the magnitude. So this is essentially what this is essentially crossing these tangent directions, taking the magnitude and then multiplying by the way that you increment the parameters, right? Correct. So now, if you think about if you think about the vector function that we actually wanted in the definition of the double integral, we actually now we have a vector, right? So this is r sub u crossing r sub v. That's a vector function that we're going to accumulate. So here we complete that the Riemann sum argument. Okay, so the area of the surface is approximated by just using a Riemann sum. Okay, so the area of the surface is approximately. So if you subdivide let's say the UV pair is in the region D. It's subdivided by m pieces along the u direction, along m pieces along the v direction. So it's going to be an index I from 1 to m, index j from 1 to n. That's respect to u and v. Okay? So now at every point we have to calculate these tangent directions. Okay? So that's going to be what? It's going to be r sub u at a particular sample point crossing r sub v at a particular sample point. Okay, so that sub-index ij here just indicates which sub-region that you're looking at, and the star just represent okay we have a sample point that we want. Okay, but then we take the magnitude as we have on the previous line, and then multiply it by delta u delta. Okay. So that's the Riemann sum, right? Basically, it's just saying, okay, at those sample points, I just calculate these tangent directions and then cross, and then take the magnitude. And then we see that everything is accumulated with respect to delta u delta v. Okay? So this part, when we convert to integrals, that's going to be du dv, right? And then these are just going to be functional expressions that we integrate, and then the double summation will become the inverse signs. Okay? So here let m and n, so the number of subdivisions go to infinity. Then by double Riemann sum, we get the formula for the area of the surface. Okay, so that's exactly the double integral on the region D of R sub u crossing R sub b. Okay, so that's the functional expression that we calculate at every pair UV. Okay, and then it's going to be du dv right here. Okay. And of course we just can replace it by just dA if you prefer to denote it as the way that you subdivide the regions. Okay. Right. So that's okay. That's the formula we want to put in the box. So you see, this is in a way really similar to the line integral when we calculate the arc length. Recall that for arc length, it's actually cap L, which equals to, so basically it's from A to B, with the range of your parameter. So recall that we had R prime of t, which is the tangent direction, right? So basically, that's a special thing here that we're integrating is actually the tangent direction if we only have a curve. But now that we want to replace it, we wanted to replace it by something called a star, right? When we were motivating the surface integral. So that star now is exactly this cross product of two tangent directions. Okay. But beyond that, everything is pretty standard. Okay. So the arc length then becomes a level integral, and then here our surface integral becomes a double integral. Okay. Another remark. So geometrically speaking, what do we have? So basically, we have a surface like something like this. Okay, so it's curvy. But then recall what we have done is that okay, you have R of UV, and let's specify the U0 V0 pair. Then you end up with just whatever point that you have on the surface, right? But then remember, C1 is the curve that forms if you only change the U entry, right? So that's C1. And along this direction, you have a tangent, which is R sub U. Right? And then the other curve that you can possibly generate is resulted from changing the parameter B. Okay? So that's C2. And along that direction, you have R sub B. Okay? And now, so the geometry here is okay. Now I have R sub U, R sub V. This cross is actually the direction that's perpendicular to these two tangent directions, right? So this is the resulted cross. So for any U0 V0 pair, R sub U cross R sub V at this data point. So if you look at this, this purple vector is actually perpendicular to the two tangent lines, right? And also, if you think about it, these two red tangent directions, they form a plane, right? So basically, this is actually the tangent plane formed by these two tangent vectors for the surface. So essentially, this cross is the normal vector of the tangent plane of the surface S as the corresponding point. . So here, now, when we talk about the cross, okay, so if you choose R sub u cross R sub v, I basically say, okay, I let u to be the first variable that I'm differentiating, and let v to be the second variable that I'm differentiating. You can decide a cross, right? But then if you switch the if you switch the order, let's say you use R sub v cross R sub u, that will give you an opposite direction. So it's this is another decision we will have to make when we talk about this lower direction. So it could be pointing upwards, could be pointing downwards. So that's sometimes something we'll need to emphasize a bit later. But this is the geometry. And here, one more thing I'd like to mention is that if R sub u crossing R sub v is not the zero vector for any UV pair in the parameter region D, we have a name for this kind of surface. Okay? So we call the surface as a smooth surface. So basically, if you cross and you get a vector, you don't want it to be zero. Okay. So if it means if it's zero, that means what? That means R sub u and R sub v along the same direction. Okay. So that's actually pretty weird. So basically, for this smooth surface, it will not have corners. Okay. So we'll be looking at the smooth surfaces in the rest part of the course. So example. So now we are given the method to calculate the surface area, right? So let's find the surface area of any sphere with radius r. Okay. So here, so although we don't really specify the location of the sphere, but we can always just choose that the origin to be the center of the sphere. Okay? So it's always nice that we convert the problem so that we start with the origin as the center. Okay? So let us consider a sphere centered at the origin. With radius r. So basically, the first step we do, if you recall, is that we need to decide that r, right? So r is the vector function to describe the surface. And there are two parameters that we want to utilize. So here we just use the spherical coordinates. Right? So here the distance, that rho is fixed. So here, the parametric equation so basically we're using so rho is r, so r sine v cosine theta, y is r sine v sine theta, okay, and z is r cosine v. Right. So r is specified to be the radius, but now we know that phi must be between 0 and pi. Okay. Theta is between 0 and 2 pi. Okay. So now we just we're talking about the area of the entire sphere. So these ranges must be chosen appropriately. Okay. So now in terms of phi and theta, you see, okay, this is a nice region. This is rectangular region, okay, in these two variables, okay. So it tells you the vector function R, so now it's in terms of, so the first variable is phi, the second variable is theta, okay, so that we decide. Okay, of course, you can change the order, so that the order doesn't matter that much here. So R of phi and theta, so in terms of vector function, we just put x, y, z components accordingly. So the leading component is always that x part, and then plus r sine v sine theta now, j plus r cosine v, okay, right? And then here, that region D that we have for the variables is actually the rectangle. So yeah, this in the set D, which is the rectangle phi within 0 and pi, and theta is region. Okay. All right. So now so if we just look back at the figure on the top of the screen, that's actually that black vector function that we have, right? But then what do we need? We need the tangent directions, okay? And then we need to cross, and then take the magnitude and into it. Okay, so we just do it systematically, and this is a very important process. Okay, this is essential throughout this section. So now we have phi to be the first variable, so let's do the partial. So basically, every component we take the partial, we start with phi, right? So we have r cosine theta, that's treated as constants, right? So sine phi gives you cosine phi when you take the partial. And similarly, we have our cosine phi sine theta, j. And then finally, cosine phi gives you a negative sign, phi, okay? And we keep that r in the front. So everything about r and theta are kept as they were because they are constant multiples, okay? Now, if you take the partial derivative of theta, so it's a little bit different because if you look at the expressions, this is about theta, this is about theta. We don't have anything about theta for k, okay? So that will give you, that will throw away that k component. So cosine gives you a negative sign. Cosine theta gives you negative sine theta. I. So sine gives you a cosine, so plus r sine p cosine theta j. And there's no k. Right? So that's good. Okay. So parameterization, it should be standard, but now this is the first important step that we do the partials. And then what do? We cross, right? Hence, r sub phi crossing r sub theta. So this is what the cross product once again. Okay, so you see why cross is that much emphasized at the beginning of the semester. So these are relatively complicated components, so let's be careful. Okay. So we have we just put the r sub phi at the second row of the determinant. So r cosine phi cosine theta, r cosine phi sine theta, negative r sine phi. And okay, that should be enough to close the determinants. The last row is negative r sine phi sine theta, r sine phi cosine 0. Right, so we do have to calculate the cross, okay? So let's just do that. So basically, we can actually write down the things in a simple manner because there's a zero here, so it very much simplifies the calculation. So basically, if you think about I, right? So it's gonna eliminate the first row, first column, and you have the order 2, and okay, the diagonal gives you a 0. Okay, so basically, this is the off diagonal. We have these two multiplied, right? But there's a negative sign, so minus the negative r sin phi times r sin phi cosine theta. Okay, so that's actually the negative sign is gone. Okay, so so r squared sine squared phi sine cosine theta. You have the cosine there. I. Okay, now minus, now we look at J. So when we look at J, we eliminate the first row, second column. And once again, so the diagonal gives you a 0. Okay, so for the off diagonal, we have what? We have negative. So these are negative numbers, negative expressions on the off diagonal entries. So this is r squared sine squared phi again, but this is sine theta. Okay. So once again, the outside negative sign is from the fact that the entry in front of J has to be negated. This negative sign is because we have two entries on the off diagonal that we are multiplying. And the result of the multiplication does not have a negative sign, okay? Because two negatives make a positive. Okay? Finally, plus in front of K. In front of K is going to be a little bit more complicated because we limit the first row, third column, right? So let me put it here. Now we have two expressions that we want to combine. So this is r squared. So the diagonal is r squared sine phi cosine phi cosine squared theta. Okay. So and we have to minus the off diagonal multiplication. Okay. So the off diagonal multiplied, you will get to negative r squared sine phi cosine phi sine squared. Right. That's good. Okay. So very important. Okay. And now we can expect to simplify at least the K component, right? Because we see here that's in common. That's in common. If you factor that out, you will get what? You will get that expression multiplying by sine squared theta plus cosine squared theta. Right? So these two, if you combine, this gives you r squared sine phi cosine phi. You do the Pythagorean theorem. Okay. So now we can simplify this vector this is a cross product, because now if you look at the expressions, what do we see? We see, okay, this is r squared sine phi squared. Okay, this is r squared sine phi squared. So at least you can take out a sine of phi as in common, right? So that's in common, so r squared sine phi. And then what do we have left? So we have sine phi cosine theta plus sine phi sine theta j plus, okay, we have cosine phi k. Right? So we do this because this is going to be helpful for us to calculate the magnitude. Okay. So what do we know about this part? This part is actually what? This part is actually the parameterization of a unit sphere, right? Sine phi cosine theta, sine phi sine theta, and cosine theta. Right? So basically, this is this circle part in purple. This actually has a magnitude of 1. Right? And indeed, we can just calculate and check. So we don't really have to repeat the process for many times, but so the constant multiplier in the front is can be taken out of the magnitude, so we just keep the absolute value there. Okay? And now for the vector part, so we just sum the squares. Okay, so sum sine phi squared cosine squared theta plus sine phi squared sine theta squared, and then cosine squared. Okay. So Pythagorean theorem once again. So that combines you a sine squared of phi, and these combines you a 1, right? Like we mentioned. Okay. So indeed, the final result here is that constant multiplier in the front, which is sine squared, excuse me, r squared sine phi. Okay. Of course, that yeah. Let me keep the absolute value here and then do one more step. So we can get rid of the absolute value because we have phi to be between 0 and pi. Okay. Since r squared is of course non-negative, and we have phi to be between 0 and pi. Okay. So that sine phi is always non-negative. And you see, this is really familiar, right? So basically, if you go back to the what you remember about the spherical wedge, right? So spherical wedge has this multiplier in front of d phi, d theta, d rho, right? So actually, this one somehow represents the surface area for that wedge along the spherical direction, because when you increase that phi to be delta phi, that the thickness of that wedge is exactly delta. Excuse me, is exactly delta rho. So that's just like something nice if you do remember. Okay, so this is a familiar expression. Thus, now we can calculate the surface area. Okay, so basically we're integrating on the double integral over the region D of this magnitude of the cross, right? And we know what that is, okay? But here, basically, so write one more line. So the magnitude is going to be the expression on the previous line, which is sine squared, excuse me, r squared sine phi, right? And then we're integrating over the region D. So this is really nice because the region D is just a rectangle, okay? So we can write it out. So to just be reminded that this is just a rectangle in terms of phi and theta. So there's nothing special here. So we just directly write down the double integral. So basically we have theta between 0 and 2 pi. That's d theta. Phi is between 0 and pi, that's dp. And then we're integrating r squared sine of okay. So now we notice that okay, r squared is constant. And then we only integrate sine phi, right? So that you can treat it as sine phi times 1. So you're actually integrating from 0 to 2 pi, you're integrating 1 d theta, and then you're integrating from 0 to pi sine phi d phi. Okay. And so this is r squared, and this is 2 pi, and okay, the antiderivative of sine phi is negative cosine. And you evaluate at v equals to 0 and v equals to 5. Okay. So the answer should be 4 pi r squared. Right. So which is what we want. Any questions so far? It's good. So this is not a simple process, but this is exactly the way that we calculate the surface area. Okay. All right, so now we established actually one of the equations of the surface areas that we want to choose. Okay, so let me quickly copy something that we have established at the beginning of the section. Okay. It's right here. So actually, we are looking at three different motivating line integrals and the three equations for the surface area, basically the first surface integral that we want to establish. Okay? And we established one of them. Let me put it here. We have this. Yeah, let me make it a little bit smaller. Right. So what do we have here? We I certainly don't want it to be that color. Good. So we started with this formula that we just established right here. Okay. So from extending arc lengths to the surface, we actually got this one. This is actually ds that we want to denote. So the notation of the way that you accumulate along the surface is actually on the ds. Okay, and that's the same here. So that's just a notation, right? You can think about it in that way. But then that the star is what? The star is that the way that you accumulate as a vector function, that's r sub u cross r sub b. Okay. And we can expect this vector function that we're accumulating within the magnitude will stay the same right here. Okay. So now, so for the second equation, that's motivated from the line integral of a scalar function f of x, y, z. So for this form, we just need to be careful about the evaluation of this function on the surface, right? But now for the double question mark, we also have this because this is what? This is just the function. Okay? This is r of uv. R of uv. So basically, this is the vector function with the two parameters. So we just do the evaluation there. That tells you what? It tells you the last surface integral can be also defined because once again, the double question mark, that's actually the vector field evaluation on the surface. Okay? And the star is a vector function. This is just r sub u plus r sub b again. So you can say this is the normal direction that's perpendicular to the surface, right? So you see, for these three surface integrals, everything is almost defined. Okay, so we have the evaluation double question mark throughout these equations. We have the star throughout the equations. Okay, and here we are just saying, okay, these are just notations that you subdivide the surface area. Okay, so that's going to be denoted as ds. Okay, so one more thing that we need to do is the vector form. So this one. Okay. So this is the vector basically related to the surface. We're going to denote as ds in the vector form. Okay. Somehow to summarize the definitions. Okay. So here for the surface integral, so we're just gonna utilize the W integral over the surface as the notation. Okay. So here the vector field just acting on the surface. So this is ds that we want to just specify a little later. So this is on the to-do list. Okay. But now, for the calculation, it's not so bad, right? Because on the right-hand side, so we are just utilizing the region about the parameters, so that's D. So what do? We evaluate the vector field on the surface, okay? And then we dot with the null vector in a sense. Okay, so this defines what? This defines the surface integral of the vector field F over our surface S. Right? So this is really similar to what you have seen for the vector field acting on a curve. Okay? And then now for the surface integral of a scalar function of f of x, y, z. Okay, so now we're just saying the notation is ds. Okay, so ds just means okay the way that you subdivide the surface area. Okay, and then the calculation like the top line we have on the screen. So this is W integral over the region D of once again. So this little f, okay, the scalar function is evaluated on the surface. Okay, so we plug in that parameterization. And then we are calculating the magnitude of the cross. And then we just do the W integral respectively. Okay? And finally, when your little f is 1, we're just calculating the area of the surface. Okay? And the formula is basically omitting that little f. Okay, so we don't have the evaluation anymore, but so we are still calculating, we are still integrating the magnitude of the lower vector here. Okay? And of course, the second integral is the surface integral of a scalar function over surfaces. Right. And the last equation is the area of the surface. Okay, so these are definitions, of course, and a few remarks. So these are pretty standard remarks. Okay, so if F is a union of smooth surfaces, smooth. S1, S2, all the way up to let's say Sn, which only intersect at the boundary. Then just like what you have seen for the line integrals, you can just somehow put up some of the unions of the line of the surface integral. Okay? So the surface integral over the entire union is going to be the sum of the individual surface integrals. Okay? So that's what you expect. And similarly for the integral of a scalar function is the same thing. Okay. So if you do this surface integral of this scalar function little f over the entire union, this is going to be the sum of the individual surface integrals. Another remark. So, from the top line about the surface integral, right here, you see that ds, okay, the way that you subdivide the surface area now directly relates to the magnitude of the null vector right here, multiplying by the way you subdivide the region D, right? And notice that this relationship took all together with the surface integral of the vector field starting with ds. Okay? So basically, the calculation here is that over the UV region D, we are doing the evaluation of the vector field, starting with R sub u cross R sub v. Okay? This is the null vector resulting from the cross, yeah, right? But now, basically, this is the magnitude of this vector, okay? So if we factor that out and replace dA by ds, this is gonna be the double integral of the same evaluation of the vector field. Now, this is starting with R sub u plus R sub v over its magnitude, okay? So this is a unit vector and it's also perpendicular to the surface. So here I'm replacing dA by ds. Okay, so this is actually what? This is actually a unit tangent vector. Okay? So unit normal. So here, if you denote it as little n, so this part becomes what? This part becomes the vector field starting with the unit normal vector of the surface. Okay. So now this part becomes just a scalar integration over the surface. Okay. So here, a little n is a very important concept right here. So little n equals to R sub u cross R sub v over its magnitude is a unit null vector of the tangent plane of S at parameter UV. The surface integral for a vector field starting with this ds, okay, this is a direction which eventually becomes this direction right here, okay, which is the null direction that's perpendicular to the surface. Okay? But here we notice that if we translate dA into ds, the way that you accumulate the surface area, then you end up with this unit null vector. Okay, but then the problem here is that this is really up to which variable, which parameter that you choose to be the first parameter. Okay, so it's really about okay, which one you use for R sub u. So if you choose a different one, then the cross will give you a negated vector. Okay, so we do want to specify a unit vector, unit normal direction n, that is regardless of the choice of the parameter. Okay, so that's why we have this figure right below. So basically, you have the surface. You depending on which variable you choose, you will be given RV as two tangent directions. Okay, representing the partial derivatives. But then which one? So is it the upward or downward that we choose for this unit normal direction? Okay, so the surface integral of f starting with ds. This now we know this equals to f starting with the normal vector perpendicular to the surface ds, where ds is just the way that we subdivide the surface area. So here, the question is which direction of n that we want. Okay? So basically, remember when we were doing the cross product, that at the beginning we were saying, okay, we choose one that's following the right hand rule, right? But here it's a little bit different, because if you think about the line integral, so we specify that the way that you increment the variable is going to be the positive orientation. Okay? So that's something related to what we do here. So this is the concept that's called oriented surface. So basically, we're looking at two-sided surfaces. Okay. Recall. So for line growth, basically when you do the line growth along the curve, cap C of f starting with dr. So dr represents the tangent direction, and we assume that the orientation of the curve is corresponding to the increment of the parameter, right? And we say the opposite orientation is going to be the negation of the positive orientation of the curve. Now, for surface integrals, the orientation is decided by the direction that you choose for the unit node vector. Okay? And the convention here for choosing the direction of n to put it in two words is either upwards or outwards. Rotation. Convention. So basically, if you have a surface that's actually that you can determine the upside and downside, I'll quickly sketch it. Let's say the surface that you're looking at is something like this, okay? So this is a figure within the three-dimensional space. And then we're looking at the positive orientation is going to be the one that's pointing upwards. Okay. The positive orientation is the one for which little n points upward or orientable. two-sided surface. So basically here, this just means that the k component of the normal vector that you calculate must be non-negative. So basically, this just means that for whatever cross that you calculate, and you can normalize it to be the little n, right? But then if you see that the last component is positive, you're good. If you see that's negative, you just negate the whole thing, okay, the whole vector. So that would be the positive orientation for a orientable. So basically, if the surface, you can decide the upside and downside. Okay? But sometimes it's not doable because you have a closed surface. Okay? So let's say a sphere. In that situation, it will be, the orientation will be the outward orientation. Okay? So yeah, so basically here I'm just sketching a kind of like a sphere. That's the surface. And then in this situation, we're gonna look at the one that's pointing outwards. Okay? For closed surface. The positive orientation is the one for which little n points outward. So basically, in this scenario, the normal vector, the unit normal vector that you calculate, the little n, either it will point inwards or outwards. Okay, so we choose the outward one to be the positive orientation. Okay, and remark. We only consider two-sided surfaces in our course. So in the real world, there's another type of surface which is called the one-sided surface, but that's not going to be covered in our class. Okay. So basically, if you think about the Mobius strip, it's one-sided actually, but that's just something in another course. Okay. Example. So let's say the surface is defined by a function, so z equals to g of xy. So basically, this is a surface that you can decide the upside and downside, right? Because this is just a functional surface, okay? This is a graph of a function, okay? So quickly sketch, let's say, what the surface may look like. So basically, this is the surface S where you have z equals to g of xy. So without specifying the axes, we get an idea. Okay. So here, clearly, since this is a functional surface, the upward little n corresponds to the positive orientation. Okay. So here we're able to try to derive the unit node vector here. So we specify the parameterization to be the standard one. Basically, we just use x and y as parameters. So we use a simple parameterization. So basically, x equals x, y equals y, and z is parameterized by x and y. Okay, so g of x, y. And here, so even though this is a really standard and a fundamental parameterization, but here we have a choice actually. So let's firstly do the order of the parameters to be x and y. Okay, so you say, okay, my first parameter among the two is x. My second parameter among the two is y. So if you do that, well, the thing that matters is the order. Okay, which one is you're choosing as the first. So that will affect the cross product. But basically, the representation of the vector function is going to be the same thing. Okay, so the I component always has x in the front. J component always has y in the front, and then k component has the z coordinate in the front. Okay, so that's g equals g of x, y. Okay. And then just remember, we just do the partials, right? We just do the partial r sub x, r sub y, and then we cross. So r sub x cross r sub y is going to be, let's quickly do that. So this is ijk within the determinant. So the first row is r sub x, right? But if you do that, this every component you take the partial derivative x, right? So that's going to give you 1, 0, g sub x, right? And then if you take the partial with respect to y for the circle, the vector is going to be 0, 1, g sub y. Okay, so you can directly calculate this determinant. It's pretty simple. So it should be negative g sub x minus g sub yj plus k. Okay, now you see the result, and okay, this looks to give you a positive k component. Okay, positive k component. So this is saying, okay, this one has the upward orientation. Upward orientation and upward direction. So now the little n, okay, so the unit normal vector is going to be the normalized vector here. So little n equals to, so basically the orientation is good. Now we'll just utilize this vector by normalizing it. Okay. And here we have the three components explicitly expressed, so we just put them under the radical. Okay, so g sub x squared, g sub y squared. Finally, we have 1. Okay. G sub y. And then in the numerator, we just put that vector here. So negative g sub xi minus g sub yj plus k. Okay. So this is the positive orientation. I need the box to be a little larger. So this is the positive orientation for the unit normal vector, okay? If you're given a functional surface. So quickly remark. Consider the same parameterization. So it's still x equals x, y equals y, and finally z equals to the functional value g of xy. Okay. But the vector function is chosen so that y is the first parameter and x is the second. Okay. So this is now y of what? Excuse me, r of yx, and equals to the same vector function expression. So the only difference here is that we now specify y to be the first variable. Or if you want to think about using u and v, so basically the parameter u used to be x, but now the parameter u is y. Okay. Equivalent. So basically x is v, y is u, and z is still g of, so now we're using parameters u and v, so in place of x is going to be a v, in place of y is going to be a u. Okay, so that's the equivalent way if you want to express the parameters to be u and v. All right, so now basically if you look at this, then so the vector function is still the same thing, right? But then we just say, okay, so y is the first parameter. So if you're doing the cross product, it's going to be the partial derivative y crossing the partial derivative x. Okay? So now the order is totally opposite. So just by looking at the previous calculation, you should expect to get g sub x for I plus g sub yj minus k to be the result of the cross. Okay, so here I see previous example for the result of r sub x plus r sub y. Right. So this vector is exactly opposite. So this is actually pointing downwards with respect to the surface. So if you follow the convention, we will have to negate this result of the cross before we do the normalization. Okay. So basically we have n to be now. So the last component is negative, so we negate the whole thing before we normalize. Right. And if you do this calculation, this follows the convention that the upwards direction is the positive rotation. And of course, if you carry out the calculation, it's going to give you this the same formula from above. Okay. So basically, now we see basically the point here is that the orientation is regardless of the preference of your parameters, right? Example. So let's evaluate a surface integral of f starting with ds, where let me make a little more space here. There's a reason for that. So here we want to specify these vector fields and the surface, okay, where cap f of xyz equals to yi plus xj plus dk, and cap s is the boundary of the solid P enclosed by a paraboloid z equals to 1 minus x squared minus y squared. And the xy plane. So to quickly sketch what it looks like, so basically we have a paraboloid opening downwards, right? So and it's symmetric with respect to the z-axis because x, y are interchangeable in this sense. Okay? So you have this kind of a paraboloid, and it intersects the xy plane at the bottom. Figure is a bit too large, I think. So let me try to shrink it a little bit. Right. So now, if you look at the surface right here, so this is the boundary of the solid, where it has the top to be z equals to 1 minus x squared minus y squared. Okay. So that's the paraboloid opening downwards, and then the bottom of the solid is actually the xy plane. Okay, so this is right here. Okay, so now if you look at the boundary, this is actually where you intersect the plane xy, which is equal to 0, and so with the surface right here. Okay, so that tells you what? It tells you x squared plus y squared must be 1. Okay, so actually this intersection is the circle, the unit circle. Right. So here we can see, okay, so this is so the boundary here, there are two pieces, right? The top piece is actually the paraboloid, which is a smooth surface. Excuse me. I want to just give a name, so that's S1. And the bottom is the plane, okay? So that's another piece that we need to consider, which is S2. Right. So basically, this is what's called a closed surface. So there's another notation which is drawing a circle as the double equal symbol to indicate that this is a closed surface. Okay. So surface integral and you need a more space here. Surface integral over a closed surface. So sometimes you will see a circle right there at the integral sign that just tells you the surface that you're looking at is closed. Okay. Right. So that tells you, okay, this is a closed surface. We have to decide the positive orientation, and it has to be outwards. Okay. So that means, okay, on the top it must be upwards. But at the bottom, it needs to be downwards. And at the bottom for S2, it has to be well, perpendicular to the xy plane. Okay? So downwards. So you can expect the top orientation, little n, is something we need to calculate carefully. But the bottom is actually simple. So the xy plane, the null vector here is just k, right? And you choose to be negative, so it has to be a negative k. Is it clear? Okay, so now let's start with the calculation. Note that we have two pieces of surfaces. So note that the surface integral on the entire surface can be split into two pieces where we have the surface integral on S1 plus the surface integral on S2. Yes, yes, with factor symbol there. And here, S1 is a surface defined by the function. Okay, so g of xy. So now that's exactly what the paraboloid, which is 1 minus x squared minus y squared. And here we have a domain, right? So we're looking at the surface, and the surface is over the entire unit disk within the xy plane. So we have the parameter xy to be within the region D, where D is exactly the unit disk. So this is all the xy pairs such that I have x squared plus y squared is upper bounded by 1. And now, based on the geometry of the solid and of course the surface, you can expect that using the polar coordinates for the W integral there is going to be easier. Okay, and S2 is the region D on the xy plane. Okay. So basically, S2 is exactly the unit disk in xy plane. Okay. So now we split the surface integral into two pieces, and we look at the first. So on S1, little n is outward and just outward. Okay. So we do the calculation. So here we utilize the formula that we have. So basically it's r sub x plus r sub y over the magnitude. The formula there is negative g sub x I minus g sub y j plus k, whole thing over the magnitude plus 1. Okay, so now we have decided the n, so we calculate the W integral. So here I'd like to quickly mention that we are deciding the direction of the lower vector, but now actually the exact expression for little n is not that required, because essentially we are trying to decide the direction of the cross and that's it. So, but here to exactly show you what actually we're looking at, let's write it down. So by definition, the surface integral equals to the vector field starting with the unit normal vector and accumulated on the surface, right? So now we plug in. So this is S1, F starting with the unit normal vector, which is from the previous line. So let me just copy it. Yes. Okay. But recall, yes equals to the magnitude of the normal vector times dA. Okay. And actually, you see that the denominator right here is exactly the magnitude of the normal vector that you calculate. Okay. So if you substitute the s right here, translating everything in terms of the region D, then the denominator and this magnitude right here will get cancelled. Okay. So basically, you're trying to just decide the direction of the lower vector. So this eventually becomes the surface integral -1 of f, now starting with just negative gx sub xi minus g sub yj plus k dA. Okay. And here, now since we're looking at dA, which is in terms of the region D, we can just replace it. And now we substitute. So recall that the vector field is yi xj ck. Okay, so this is on the region D of yi plus xj plus zk. So that's the vector field. And also recall that z is 1 minus x squared minus 1 squared on the surface. Okay. And now we start with the lower vector having the expression right above. Okay. So negative g sub x. Okay, so negative. So g sub x right here. So we're taking for the red functional expression, we're taking the partial with respect to x. Okay. That's actually negative 2x. Now minus. Now g sub yj. So g sub y taking the partial with respect to y is negative 2y. Finally plus k. Yeah. Right. So it's good. So basically here, we try to express the integrand in terms of x and y, okay? And we just do the dot, and it's gonna be component-wise. So it's gonna be the double integral over the region D. And here we have, you're talking I and I is gonna be y times 2x. You got j and j is gonna be x times 2y, so that's 2xy plus 2xy for the I and j components starting together. And then for k, it's gonna be the functional expression times 1. Okay, so plus 1 minus x squared minus 1 squared. Yeah. Okay. And now up to this point, it's gonna be not hard to calculate. So essentially, we see we're just integrating over the unit disk where our function that we're integrating is 4xy plus 1 minus x squared plus 1 squared. Okay. And here we just recall that D is the unit disk. Okay. And then, of course, when we calculate it, we can just utilize the polar coordinates. So basically, we have theta between 0 and 2 pi, d theta. And then for r, now the radius is 1, so from 0 to 1. So make sure to have r d theta. Okay, so remember there's a radius right there in place of dA. And now for the integrand, we just substitute x and y as r cosine theta and r sine theta. Okay? So this is going to be 4 r cosine theta times r sine theta and plus. Now this is going to be 1 minus x squared plus y squared. Okay, so that's actually r squared. Right. So let's quickly go over the steps of doing this calculation. So essentially, you need to multiply things out and just distribute that r at the end. Okay, so this is going to be 4r cubed cosine theta sine theta plus r minus r cubed. That you're integrating with respect to r and then theta. Okay. So to quickly do this. So the answer in terms of r is going to be r cubed r to the 4 cosine theta sine theta. So add 1 divide. So add. So this is r squared over 2 minus r to the 4 over 4. Evaluate at 0 and 1. D theta. Right. And we see, okay, the evaluation at 0 gives you nothing. So this becomes the integral from 0 to 2 pi of cosine theta sine theta plus, so 1/2 minus 1/4 is 1/2. Okay. D theta. All right. And whenever you see an r power of sine or cosine within this kind of a trig integral, you can just utilize one of the one with the r power to be the variable u. Okay, so in this case, either one is fine. Okay. So let's say u equals to sine theta, then du equals to cosine theta theta. Okay. Let's do that. But here, if you're familiar with the process, you can directly write down the antiderivative, which is 2 sine squared theta. And then 1/2 gives you 1/2 theta. Okay. And you evaluate at 0 and 2 pi. And you realize that sine of 2 pi and sine of 0, they both give you zeros. So essentially, 1/4, 1/5. So sometimes when you're talking and writing, it's easy to make little mistakes. But okay, so that's 1/4 times 2 pi minus 0. So that's actually pi over 2. And with that. Right. So you see, I would say for this kind of surface integral, the essential part is really the setup of the null vector. Okay. So somehow you need to have the positive orientation of this null vector so that the last component is upwards or outwards depending on the way that you describe the surface. Beyond that point, everything is pretty standard. Right. Remember, we also have this second part of the surface, which is S2. Okay. So on S2, it's actually much simpler because we are looking at S2 to be the unit disk on the XY plane. So once again, we have F starting with N, accumulated over the subdivision of the surface area. But now, so S2 is actually the disk, right? And here F, if you recall, that's actually yi plus xj plus zk. But on the xy plane, z is a 0. Okay. And now we're starting with the null vector. The null vector here is pointing downwards because this is the bottom, right? So n is actually negative k. If you're choosing the unit null vector. And by looking at the dot, you can expect to get a 0, right? So regardless of the xy coordinates, you are having 0 times k in F and the negative k in the vector that you're dotting. So this is a 0. So the integral is a 0. Okay. So you can conclude that this surface integral of F starting with ds on the closed surface S is actually just pi over 2. So from the previous calculation, we can notice that we don't really have to explicitly calculate the little n. We just need to specify the correct orientation of this null vector, okay, ds. So ds equal to the cross times dA in this example, where the direction of the cross is along the n. So basically, we chose the null direction to be the one that's following along little n, in the way that the last component is non-negative. Okay. In fact, if S is described by the vector function R of UV, where the UV pair is within some region D, then we can explicitly write down the rule of integral of f starting with ds to be the double integral over the region D of the vector evaluated along the vector function, starting with r sub u crossing r sub v dA. So this is the formula we have seen, which is the resulted from the motivation of our surface integral, right? But here we just need to specify that the orientation must be along the little n. Okay, so this is the same direction. As little n, okay, by convention. Okay, so here by convention, it just means we are choosing the upwards orientation for the orientable surface, or outward orientation for closed surfaces. Okay, so everything is pretty standard except this one. The orientation is the one that we need to be very careful about. Okay. Right. Another example. So just now we were looking at the closed surface, but we have two parts, right? There's a part which is a paraboloid, and then there's a plane that's at the bottom. Okay. So now let's compute once again a surface integral on a closed surface, but our surface here is the sphere. So here the vector field cap is zi plus yj plus xk, and the surface is the unit sphere. X squared plus y squared plus z squared equals 1. Okay. So quickly recall, we need to parameterize the sphere, okay? And here, of course, it's going to be a sphere, so we utilize the spherical coordinates. So parameterization of the sphere is basically, so we have the radius to be 1, so the rho is 1, so it's going to be sine phi cosine theta, y equals to sine phi sine theta, z equals to cosine phi. Okay. And we have phi between 0 and pi, theta between 0 and 2 pi, right? So that's the parameterization. Okay, so here specify that rho is actually just well. And actually, we have done the calculation of this kind of parameterization for r sub phi, r sub theta, and the normal vector already. Okay, but now here, once we rewrite it again, consider the vector function to be r of phi theta. So that's just putting the x, y, z components all together. So we have calculated already the cross of r sub phi, r sub theta. So make sure to do that yourself once again. So the only difference here is that we have a radius 1. So in the previous example that we have done before, that has a radius cap r. Okay, when we are trying to calculate the surface area of a sphere, right? So if you recall, the cross is actually parallel to the vector function. So this is parallel to the vector function, and the magnitude in the front is actually rho squared sine phi. Okay, and here rho is 1. So see previous example on surface area of sphere. Right. So we know the result of the cross, then we know the magnitude of the cross, which is exactly that sine of phi in the front. Okay. So this tells you what? It tells you the normal direction, if you calculate, is going to be the normalized vector. So basically you have this expression right here that is just canceling that sine of phi in the front. Okay. And what do you know? So if you look at this normal vector, so this is actually pointing outwards of the surface, okay, of the sphere. So let me quickly sketch that figure for the sphere as an illustration. So basically, what do we have? We have the units of a sphere right here. Okay. So this is x, y, z axis. Okay. So now the vector function is the one pointing like this, right? So basically, this is r of phi theta, right? And at the same time, notice this expression is exactly the same as the normal vector. Okay? So the normal vector is actually pointing exactly the direction along the black one, right here. Okay? So r equals to the n. So basically, it tells you what? This tells you the normal vector that we're looking at is exactly the same as the parameterization, and it tells you this cross as the normal vector is actually the one that you utilize when you're doing the dot. In other words, the parameterization of the vector function of the sphere should be the positive representation. Okay, and as long as we decide that, we'll be able to calculate the circuit integral. Okay? Thus, so for this closed surface, which is kappa to denote the sphere. So kappa starting with ds, this is. So basically here we have phi and theta, and then now let's call this region D again. So the region D here is basically all the pairs phi theta such that my basically here is the spherical coordinates, but now we have the radius to be 1, but phi is between 0 and pi, theta is between 0 and 2 pi. Okay. Just remember the definition difference between theta and phi. Okay, theta is the rotation about the z-axis. Okay, so it could be anything, but then phi is the angle that you got between the positive z-axis with your and your ray that's going through the point. So it's always an angle that's less than pi. Okay. And then just recall, if we want to translate everything in terms of phi and theta, then we need to do the evaluation of the vector field. So this is going to be R of phi theta. Okay. So this is a very important step. Okay. So basically x, y, and z, they're all going to be translated in terms of phi and theta. And now for the dot, we have decided this R sub phi cross R sub theta is the direction that's outwards. Okay, so that's the positive orientation. So we're gonna use that as the normal vector. Yeah. Right. Okay. So that's the critical part. And then we just need to do the evaluation. Okay. So evaluation and then just auto fill out the lower vector and then we can just plot. We can just dot. So just recall that the vector field is nothing but zi plus yj plus xk. Right? So basically here we need to be careful because for the evaluation we need to translate xyz in terms of theta, theta. Okay, so it's the spherical coordinates. So translation. So basically we can write the double integral in terms of phi and theta. So here let's see, phi is on the inside, theta is on the outside. So theta goes from 0 to 2 pi. Phi goes from 0 to pi. So d phi d theta. Right? So that's dA. Since the region D here is just a rectangle in terms of the angles, okay? So that's dA. Well, this evaluation could be long, right? Because F it has 3 components, and every component is somehow complicated. Okay, so to recall, we need to write everything in terms of vector form. Okay, so Zi, right, for F is Zi and Z equals to a cosine phi. And then that's I plus, and Y is sine phi sine theta. And then X is sine phi cosine theta. Okay. Just now you see ZYX, the order is flipped. So and then we have the other vector as the lower vector that we just decided. Okay, so basically I can copy it down from the above, but here I just want to write it again. So just remember when we were doing the cross, it's a scalar sine phi in the front of the spherical description of this the surface. Okay. So that's called sine phi cosine theta. Just once again. So the more that you write for the spherical coordinates, the less likely you will get mistakes. Okay. And then plus cosine. Right. So now we have the evaluation of the vector field in the previous line, and the normal vector that we decided for the second line, and then we follow by dA, which is in place of replaced by d phi d theta. And then we just need to simplify and calculate. Any questions so far? So if it's good, then we just do the dots. So be careful. We see that we have two vectors and there's a scalar sign of phi there. So that the following arithmetic specs is very important. Okay. So from 0 to 2 pi, from 0 to pi, and then d theta. So notice that here, basically, this is actually what? This is actually x, y, z. This is actually zx, zyx, right? So basically, you have what? You have zx plus y squared plus and plus xz, right? And then whole thing multiplying by sine of phi. Okay? So that's somehow you should have a 2 times xz eventually, and you have y squared eventually. Okay? So xz is sine phi, cosine theta, right? And now multiplying by sine is sine phi in the front is sine phi squared, cosine phi, cosine theta, and there's a multiple of 2. Plus, now for the component y, it's gonna be squared, so it's gonna be sine cubed phi. Okay? So sine phi, and this is sine phi again. Make sure to not miss the distribution of the multiplication. Sine squared theta. Okay. And now you see, okay, this is beyond this point, there's nothing but the trigger intuitions, and you see why trigger intuitions is critical in Calc 2. Okay, so because essentially in this kind of spherical computations, there's a lot of trig functions involved. Here, basically, once again, let's point out that if you split these functions, so cosine theta is easy to integrate, right? And here you have sine squared theta. That's you can translate by converting it to 1 minus cosine 2 theta over 2, whole thing over 2, right? And then this is a sine phi to the 3. This is a cosine phi to the 1. So these are all powers tells you that you should use the other variable as the other expression as u. So you should choose sine to be u here. This is cosine to be u here when you're doing this u substitution. And so those steps, make sure to calculate. And here I'm going to just give you the answer that you can verify. And it turns out to be 4 pi over 3. Okay, so which is a nice number that you have seen before. Right. So basically, this constant it seems to relate to the volume of the sphere, right? So here, a very important remark regarding the previous 2 examples. In the previous 2 examples. So let's quickly capture the problem statements and the figure. Okay. So actually, if you look at the vector field, so let's quickly look at what we have seen before, the one before, the example before this is this one. So let's copy the thing. So basically, if you look at the vector field, this is yi xj zk, right? So if you're trying to do the divergence y gives you nothing because it's in the first component, x gives you nothing. But z gives you the del z that's giving you a 1. Okay, so divergence in this particular example is 1. And it's also true for the second example right above. So here, I'm trying to put the 2 examples on the sides. So basically here, we're trying to integrate a closed surface on the closed surface f starting with ds. And here, let me quickly mention what are we looking at? Basically, we have a vector field, and we're starting with the orientation that's perpendicular to the surface, and it's pointing outwards, right? So this is called the flux integral when we're looking at the closed surface, right? And now, if you look at the calculation, this is on the closed surface, we're having f starting with the unit normal vector that's perpendicular to your surface, holding integrated over the way that you accumulate the surface, okay, the subdivided surface, the subdivided surface area. So f starting with n is a scalar function, okay? And we summarize that the answer was pi over 2. But now, so in the previous example, we have 4 pi over 3 right there, so it somehow relates to the volume of the solid. So actually, that's true because once again, we note that the divergence of this vector field is actually 1, right? So once again, so the vector field on the top is yi xj zk. So del y del x is 0. Del x del y is 0, del z is 1. So divergence here is 1. So we were doing this flux integral over the boundary surface, and it gave us pi over 2. And if we try to integrate this divergence over the entire solid that's contained by S1 and S2, it's actually not so difficult. So we're going to do the triple integral over the solid, which is, of course, just enclosed by these surfaces, okay? And we accumulate just, we just integrate 1. That will give you the volume, right? So, and now, once again, the region, if you project onto the xy plane, is going to be the region D, which is the disk. And then you are integrating what? You're integrating the upper bounding function minus the lower bounding function over the entire region, accumulated in terms of the way that you subdivide the area, right? And this D is exactly disk with the radius 1. Right? So this is a really simple polar coordinate example that you can do. And indeed, this volume is pi over 2. Okay. So this should be easy to calculate, so I'll leave this to you guys. So in this example, you see, okay, it seems like this flux interval, the flux interval you evaluate right here agrees with the accumulation of the divergence over the entire solid. Okay, and actually that's true also for the previous example that we just did for the sphere. So let me copy that example down also. So the statement of the question is right here. And I also need the figure, but right. So once again, if now I'm copying, and if you look at the if you look at the divergence, it's the same thing, right? Yeah, I need to make it a bit smaller. And I need the figure. So for the previous example, the divergence is also 1, right? If you do this calculation right here. So it's zi plus yj plus xk, right? So del z del x is 0, del y del y is 1, del x del y is 0. Okay. So to summarize, we have the flux integral over the surface. We are integrating f starting with ds again, and by definition, this equals to f the integral of f starting with the unit normal vector that's pointing upwards. And the scalar function that we have, we integrate over the surface, or here the sphere, accumulated with respect to the area. So this result was 4/3. And also note that we mentioned just now that divergence here is also 1 for this vector field. Okay. But here we don't really have to calculate the volume again, because we know for a unit sphere, the enclosed ball has the volume of 4π/3 times the radius cubed. Okay. So it looks like for this flux integral, it's also giving you the same effect that you're accumulating the divergence over the entire solid, right? So here, for both examples, it's from these two examples, it's tempting to have this kind of speculation that in general, if you have a closed surface and you're calculating the flux integral, it may relate to the accumulation of the divergence over the entire solid. Okay. So this somehow motivates the rest of the sections in this chapter. So here, this one is the integral over the boundary of what you of the object that you're looking at, and namely the flux integral over the surrounding surface, right? And this right-hand side is actually the integration over the entire object that's enclosed by the surface. Okay, so indeed they are related. So in the three-dimensional case, this relationship is called the divergence theorem. Okay,